we talk about maximum permissible velocity, then we must have some idea that, well, for this particular non-alluvial formation, what can be our maximum permissible velocity? Once we know that, then it is not a difficult task for us to calculate the velocity, because using uniform flow formula, once we decide about a shape, about the size of the channel, once we decide that, then say getting the value of velocity or computing the value of velocity by using Manning's formula, say v is equal to 1 by n, then r to the power 2 by 3 s to the power half. This is very common. Once we know the slope of the channel, once we know the dimension of the channel, means r will be known to us, then velocity we can compute easily. But what information is required is that which velocity is permissible or which velocity will remain within limit for a particular material. And that we can see that this table is giving us some idea. That is, for lean clay soil or loam, this ranges from 0.38 to 1.37. And for clay, it is from 0.41 to 1.67. Of course, as you can see, the range is very high. So for velocity value is concerned, the range 0.41 and 1.67 is not a very small range, and these are in meter per second. So this range is still quite large. Experience count at that point. And looking into the situation, we should know that what can be the value of this. And in fact, sometimes we may have to go for experimentation also to know the exact value. But for, say, design of a small channel section, we may take this value and we can go by this permissible value. And when we are not sure about what will be the maximum value, then we should go for the minimum value, what is being suggested as the maximum velocity. Because range can be from 0.41 to 1.67 for clay, say. So if it is clay, if we do not have much idea, we should be conservative in our design, and we should use then 0.41 meter per second as the value. Because if we take this higher value, then we may not be sure that at lower than that also the clay surface can get eroded. Well, then for heavy clay, it will range from 0.45 to 1.7. For sandy clay, when we are coming to sandy clay, then it is ranging from 0.52 to 1.83. Then muram, it is going from 0.6 to 0.9. Here range is little less, and we can be more confidently we can use. For hard muram, in fact, it is giving us 1.2 more confident. Then gravel is giving us 1.5 meter per second. Boulder, when it is of the size boulder, that is little larger size, then this can be taken up to 1.8. Soft rock, 1.8 to 2.4 meter per second. And if it is a hard rock, as I was stating earlier, that for cement concrete also we can take up to 3, and for hard rock also it is 3 meter per second or greater than 3 meter per second. It depends on what type of rock it is. And of course, the chemical composition of the, mineral composition of the rock matters. Because when we are talking here about the strength of a rock, it is always in connection with water. So it will be in touch with water. Then how it gets weathered under the action of water, that is also important. So the mineral composition of such hard rock also we need to know, because today it may remain very hard, but with time it may undergo weathering, and then due to weathering its strength may reduce, and with time it may deteriorate. So that way these are the value. Now again, this is one point we are getting what is our maximum velocity. Then before designing, we should know one more aspect. Say a channel we want to design, then from the topography we are getting the slope, fine. Then what should be the side slope of the channel? Whether it is we can go for rectangular, whether we should go for trapezoidal, that we are not knowing at this point. Well, so that is also one important aspect that we should know, and from experience and from experiment we can find out this sort of value, And these were given as suggestion like that for clay. We can go for a slope of 1:1 if it is in cutting. What we mean by cutting, that as I was explaining, say suppose natural terrain is like that, and we want to make a channel to carry something from say this point to this point, water. Now it will be difficult to go like that, so what we will do, we will make an average slope like this from here to here. We are filling up this portion, and suppose this formation is clay. So this formation is clay. Then what we will be doing, that we will fill up this portion and we will cut this portion. This portion will be say under cutting. This portion is under cutting. And this material that we will be getting by cutting, that can be filled up here to get filling portion. So this is what the filling. Now definitely when we are having a filling portion, here the clay, although it is the clay material, but will be in little loose state. Although we will be trying to compact that, but still the in situ condition of clay will be definitely less, will be having less strength than the, will be having more strength. In situ condition will be having more strength than the filling condition. So that way, for the portion where we are having cutting in clay, there we can go for side slope of 1:1. But if in the filling portion, we should not go for that sort of steep slope. We can go for 1.5:1. Then of course, when it is grit, then we can go for 0.5:1. And then if it is soft rock, these are, we are talking about cutting, soft rock, then it is 0.25:1. That way it is increasing. For hard rock, we are going for 0.125:1. And in fact, for hard rock, we can go for zero slope also. I mean, zero slope means it is vertical. 0.125 is also very small. Say it will be like this. 0.125 is also like this. Means almost vertical. Almost vertical, say this will be. And in some case, we can even go for vertical cut. Well, so these are some information which we can use for design of this canal in non-alluvial channel. And what will be the procedure, design procedure? Say bed slope we will be getting from the topography as I have explained. We have very small scope of manipulating that. Of course, we can do it as I was showing here, that say this can be the slope, we can have this slope also by cutting. We can have, if we cut this portion, we can have this slope. If we fill up this portion. So slight manipulation is possible, but grossly we cannot change the slope. But still, okay, bed slope we will be knowing from the say topography. Then the side slope. This last slide will give us the side slope based on the material or based on the formation material. We will be deciding our side slope. Well, then the discharge that we will be getting by hydrological analysis. Or suppose hydrological analysis means if it is a drainage channel, we need to know how much surface runoff will be coming. And that way we can decide how much discharge will be there. But if it is an irrigation canal, then it will depend on how much water we are releasing from the main source, or what is the water requirement of the crop. Based on the water requirement of the crop, we will be releasing water. And what is the maximum requirement of the crop water, that we will have to find out. And of course, with that, we need to aid what will be the loss and other aspects. So that way, how much maximum discharge we are allowing to flow through the channel, or we will be allowing to flow, allowing through the channel, we need to know. So by some means, we need to have our discharge. And that part, of course, we are not discussing right in this course. And then Manning's N, that is the roughness parameter. Roughness parameter we need to know from a characteristic of bed roughness and characteristic of site roughness. And in many standard book, now this Manning's roughness value are available. That part we did discuss in our discussion regarding uniform flow. So, and we are not discussing it here again, but we can have this value from standard book, and many references are there. So this will be generally known or can be obtained, as I have explained. Then after having this thing, we'll have to assume a permissible velocity. So say V is known. What should be V? Or sometimes rather than having that V, we can have, rather than having that velocity V, we can have, or we can adopt a B by Y ratio. That is width to depth ratio. And some suggestions are there, some organizations has worked, and for a particular discharge, what should be the B by Y ratio, that sort of some table or graphs are available that also we can use. Of course, this is more convenient. And then once we have this V and the charge, we can compute the area. So this area is known. Then here we can see that now we can use Manning's formula and we can solve for the width B and depth D. Because we need to know, design of channel means we need to know what is the bed width and what is the depth of the channel. So we can now use Manning's formula and we can solve for this bed width and D, because the area is nothing but a function of B and Y. And its velocity, by using Manning's formula, what we can have, that 1 by N, then A by P to the power 2 by 3, and SB to the power half. Now SB we already know, and we are knowing, so V is a function of area and perimeter. Then area and perimeters are nothing but these are just expression that this area and perimeter can be expressed in terms of B and Y. So this is also a function of B and Y. So we have two equations. We have two equations and we have two unknown, B and Y. So these two unknown can be solved from these two expressions. And that way we can have our design dimension. Well, and then with this, now we have that understanding how we can go for design of alluvial section. So then of course I did not mention that if we go by the value of B by Y ratio, if we go by the value of B by Y ratio, once we have this B by Y ratio, then this velocity or area, whatever we calculate, say our B by Y ratio is given. So then velocity, as it was a function of V and Y, B and Y, or say area, that was a function of B and Y. Now what we can have, velocity, this when B and Y ratio is given, so B itself is, suppose B by Y ratio is suppose 2. Then we can have B is equal to twice Y. So B itself is becoming a function of Y. So as such, this expression from this relation, what will be having, B become a function of Y only. V become a function of Y only, because B also is becoming a function of Y. And so from this expression, we can calculate directly the depth. And once we can calculate the depth value, this is known, then again from B by Y ratio, we can calculate the Y. This will give us Y value. Well, so the size of the channel will be known. Then we can calculate area and we can find out the velocity. But so this is also a procedure that we can follow once the B by Y ratio is given. But only one problem is that when we are using B by Y ratio, then we are getting the velocity. We are not starting from the velocity. And once we get the velocity, we need to check whether this velocity is below the maximum permissible velocity. Otherwise, if the velocity is high, we need to adopt another B by Y ratio, and we should try for solving. Well, with this, we can now move on to the topic of design of alluvial channel. Well, we started with design of say line canal. Then we have discussed the design of non-alluvial channel, and then we can move on to the design of alluvial channel. Well, now for analyzing or for designing alluvial channel, as we are already explaining that part, that's covering, that is the erosion and deposition, both can be there. So concept of critical velocity is applied for design of alluvial channel. And then when we are using this term critical velocity, I repeat that point, that critical velocity is not the critical velocity that we were discussing when we were discussing critical flow. Because we were also telling that when the flow is in critical condition, by critical condition at that time we were meaning that Froude number is 1, energy is minimum. So that sort of conditions were there for critical depth. And the flow velocity at critical condition we referred as critical velocity. When it is higher, then we talked as supercritical. When it is lower than critical velocity, then we talked it as a subcritical velocity. But that critical velocity is quite different from this critical velocity that we adopt for design of alluvial channel. Well, this critical velocity is that velocity which will neither cause erosion nor cause deposition in the channel. Well, and to have that velocity, it is very difficult really. And then several silt theories are there. And different persons started working, different investigators started working, engineers started working on this because of their practical problem in agricultural field. Basically, it started with agricultural field. So they found that in agricultural field, when canal were constructed with some expectation that it will be able to carry this much of discharge, then later on it was found that no, deposition is taking place in the channel. And then, that is of course important. Let me just explain it a little bit. When a canal was designed, suppose it was expected that this much area is there, this much area is there, flow area will be there, and sediment deposition has taken place, so its capacity has reduced. Now its sectional area remaining is only this much because of sediment deposition. So when the capacity reduces, then suppose we expected that this much water will be carried, but it will not be carried. This is one point. Well, that we could understand. But if scouring take place or erosion take place, then what is the problem? Well, if the canal was designed like that and scouring has taken place, so the canal has taken a shape of this one. Now, with a given discharge, earlier it was expected that the water will be flowing at this level. Now we know that in a canal, if we expect that this is the water level, then with this water level, it can move up to, say, okay, there will be a slope here, and with this water level, it is moving up to certain depth, up to certain distance. Here, depth will gradually come down, and it is moving up to certain distance, like that. We can show more explicitly this point that if we just draw a slope like this, and then depth is like that. So here we have, because from a river, okay, let me draw it.
Okay, so he agree with what